Welcome back to Future News. As always, an article link on this amazing discovery will be in the description below. Now, imagine a state of matter so cold, atoms merge into a single quantum entity. This is the world of Bose-Einstein condensates, or BECs, near absolute zero. BECs are not typical solids, liquids or gases. They are the fifth state of matter, a quantum mechanics marvel. Predicted by Bose and Einstein in the 1920s, they theorized bosons could collapse into their lowest energy state. This makes them occupy the same quantum state, first realized experimentally in 1995, earned Cornell, Wieman and Kettle the Nobel Prize in 2001. To understand BECs, we need to delve into the world of bosons. These particles are the social butterflies of the quantum world, happy to share the same quantum state with one another. This is in stark contrast to fermions like electrons, which are bound by the Pauli exclusion principle, a quantum rule that forbids them from occupying the same state. This social nature of bosons is what allows for the formation of BECs. As the temperature drops, bosons begin to lose their individual identities and start behaving as a single coordinated entity. It's like a group of dancers suddenly moving in perfect unison, their individual movements merging into a captivating collective dance. This collective behavior gives BECs some unique properties. They can exhibit superfluidity, flowing without any resistance, and can even slow down light to a snail's pace. These bizarre properties make BECs a hotbed for scientific exploration, offering insights into the fundamental nature of matter and the strange rules that govern the quantum world. In a groundbreaking experiment, scientists at the University of Bonn and RPTU in Germany created a one-dimensional Bose-Einstein condensate using photons, the particles of light. This might seem counterintuitive, since photons are massless particles that are constantly moving at the speed of light. However, under the right conditions, even these elusive particles can be coaxed into forming a BEC. The researchers achieved this feat by trapping photons between two highly reflective mirrors placed a mere micrometer apart, creating a tiny cavity known as a microcavity. Inside this cavity, a special dye solution was excited using lasers. When photons collided with the dye molecules, they lost some of their energy and cooled down. This cooling process continued until the photons reached a temperature low enough for BEC formation. To confine the photons to one dimension, the team introduced microscopic protrusions on the mirrors. These protrusions acted like tiny walls, creating a quantum gutter that guided the photons along a single line, effectively creating a one-dimensional beck of light. Section 4. Dimensionality, a balancing act. The dimensionality of a Bose-Einstein condensate, or BEC, plays a crucial role in its behavior. In two dimensions, BECs have a well-defined condensation temperature, the critical point at which they transition from a gas to a condensate. However, in one dimension, things get a bit more complicated. This is because thermal fluctuations, random changes in energy, have a more pronounced effect in one dimension. Imagine a line of people trying to stand still. It only takes a small nudge from one person to disrupt the entire line. Similarly, in a one-dimensional BEC, thermal fluctuations can easily disrupt the delicate balance of the system. As a result, the phase transition in a one-dimensional BEC is smeared out. It doesn't happen abruptly at a specific temperature. Different regions of the gas can exhibit different behaviors, making them more complex than their two-dimensional counterparts. Despite this, the one-dimensional photon gas still exhibits quantum behavior, albeit with a messier phase transition. Section 5. A new frontier in quantum optics. The creation of a one-dimensional photon gas BEC is a significant achievement, opening up new avenues for exploring the quantum world. It provides a unique platform to test theories about one-dimensional quantum systems and study the effects of dimensionality on BEC properties. But the implications of this research go beyond fundamental physics. It could pave the way for advancements in quantum technologies, including quantum computing and communication. The unique properties of one-dimensional BECs, such as their ability to control light at the quantum level, could lead to the development of novel optical devices. Imagine lasers that operate with unprecedented precision. sensors that can detect the faintest signals, and communication networks that are impossible to eavesdrop on. These are just a few of the potential applications of one-dimensional BCs in the field of quantum optics. As scientists continue to unravel the mysteries of these fascinating systems, we can expect to see even more exciting breakthroughs in the years to come.